thing is satisfied, we call this alternating series, and alternating series test is that they all converges to something. Alright? And they have this curious statement. Error made in approximating the sum up to n is less than the last term, or one more term in there. Right? But the statement is there, everybody understands the statement, so let me explain why this is true. I really like their idea. Instead of writing it like that, I'm going to write it like this: b1 and negative b2, b3, negative b4, like that, and where all the bk's are positive quantity and bk is really going down. So bk is all positive, and I'm throwing in the positive negative in there. So up to partial sum, for example, I'm just going to use a number. I think it's easier. If you go up to 20, what do you see? b1 minus b2, right? b3 minus b4, and you repeat this pattern all the way up to where? b19 minus b20. Correct? So if it is grouped like this, and you want to see, oh, can I group it like this and say something about the property of this S20? These are all positive number, right? Why is that positive number? b1 minus b2? Decreasing, right? Decreasing. So b2 is actually smaller quantity. So I'm adding one number, another positive number, and another positive number, right? If it is b21, I mean S21, how does that end? Here's a b19, b20. Here's b21 again, but that's positive number, right? Even that was odd numbers, is always increasing as we go in there. Alright, so if you keep going forward, then what do you have to do next to show that it actually converges? You have to found that wall that never passes. That's what you have to show. If it's keep going forward, and if you can show you cannot pass that point, but what theorem guarantees that this converges? Yeah, monotone sequence theorem. So I want you to look at this S20, really hard look, and come up with this is not going to pass this number. Anyway, it's not something that I'm expecting that you can come up with in 5 seconds, but you might. It's about grouping. If you can regroup it, and you begin to see it. So S20 again. You see different grouping? B1 here. Can you group B2 and B3? Like that? How's the sign go? So what is the correct sign for B3? B2 must have negative out there, right? This one? Negative again. Negative, negative, positive. So what do we know about this guy? Positive, right? B2 is greater than B3, but here, negative. So you're subtracting it. Let's go look at the next group. That's positive again. Subtracting it again, all the way. So how does that end? It ends with odd, so that must be B18 minus B19, right? Subtracted it. Hey, lucky, you subtracted it again, right? So what is it? It will never pass what quantity? Starting with the B1, smaller, smaller, smaller. But in what it says, keep going forward, right? But it never passes B1. Always less than B1. That's all they needed. It keep going forward, it never passes B1. But monotone sequence theorem, it converges. So let's try S21, B1, B2, B3. How does that end? 21 there, 21. So we have one more, B20 minus B21. So that's still negative. So that's still less than B1. So they're arguing that no matter what your Sn is, it'll never pass B1.
Right, let me state these observations in slightly more general way. So here's kind of a summary. We looked at even number of terms so that it groups nicely. So the first two elements, first two terms, and the last two terms group nicely, realize that all these positive terms. So what that really says in terms of using this monotone sequence theorem is the following. So if you look at partial sum ending at the even term, and if you look at the next even partial sum, we're always adding this ending up as positive numbers. So here's the partial sum ending at the even number of term, and we're adding one more. So this is increasing. So it is not really Sn, but is kind of subsequence, nth partial sum. So if you group it like this, it's increasing in a monotone. And we just saw that no matter what your index is, always less than B1. So with that much of information, we carefully conclude, because of the monotone sequence theorem, S2m converges to L, not Sn. Right? If you look at the partial sum, skipping the even odd indexed partial sum, they converge. You have to carefully state that what happens about the odd partial sum. That's why I'm redoing this. I was sloppy in the original video. All right, here I am stating, relating to the general terms here. All right. So Sn in general, if you look at an arbitrary partial sum, is either even index partial sum, so it can be rewritten as subscript 2m if n is even, and if it is odd, you can look at up to even partial sum plus one more odd term. So if you have a b subscript 2m, the next term will be 2m plus 1, and the sign, the positive negative part, if it is odd index last term, this is always a positive. That's one of the key things when n is odd. So n is either even, and n is 2m plus 1. Right? The situation is n is approaching infinity. What happened to these terms? If they have the same behavior in here and there, and that's what we want to show and conclude. So when we send n to infinity, you have it is actually parameterized by this m with the two different indices, and I don't think it's hard to see if n is like that. As n approaches infinity, m must approach infinity as well. Don't look at it as m is approaching infinity and therefore n is approaching infinity. I particularly emphasize in here is the independent parameter here is n, and m is a dependent. It depends on your choice of n. It's either this case or that case. As you can see, m, it has roughly the half of the size of n, so n is approaching infinity. M must approach infinity here. We established facts about this behavior of m, and that's where we're using it, and particularly emphasizing that n should be the independent variable here. All right, let me pull up a little bit. And here as n approaches infinity, as we have noticed, m approaches infinity, and if it is either case, Sm is almost L. If it is that case, S2m is almost L over here, and over here is S2m is almost L as well, because we showed that S2m is approaching L, and the key thing is that this additional term that made us to consider this the case in two different ways, actually approaching 0. That's one of the conditions in alternating series. These individual terms, its magnitude is approaching 0. So either you're in that case or that case, they both approach 0. So altogether, it's approaching L. This one approaches 0. So let me say that again. In both cases, they both approaches L. That's what I wanted to say. Right, here it is. So out of all that analysis, we conclude the same thing, that as n as an independent parameter approaches infinity, and however in what fashion, this Sn is going to be always approaching L because of this further analysis. So rather than just concluding and jumping into conclusion, oh, this observation is enough, rather than doing that, we analyze it carefully, using this in different cases, and try to conclude it a little bit more carefully than relying on intuition. Right? That's one of the things we do in mathematics. Thanks for watching.